Okay. Okay, Assalamualaikum. A very good morning. I bid to distinguished guests, fellow audience, and also to the hardworking event committee. Thank you very much. My name is Akmal, and I will be presenting what is currently part of my research progress. So we'll start. We'll start with the introduction, a little bit of introduction. Dielectrophoresis, by definition, means the phenomenon where a force is exerted on a particle when being subjected into a non-uniform AC current. You need to remember that. Okay. Dielectrophoresis or DEP is a fairly complicated subject. So instead of trying to explain to you the full detail of DEP, I will just show you the closest mosity factor. Okay, closest mosity factor or the CMF curve. The CMF curve is everything in dielectrophoresis. It's the what we call the bread and butter, the heart and soul of DEP lah. So everything that you need to know about DEP is in this curve. Okay. So few things that you need to know about CMF curve. One thing, I repeat the definition. It's a force that exerted on a particle. So the magnitude of the force or the strength of the force is represented by the CMF value. So illustrated by the curve here. So basically saying from lower frequency, the force is stronger and then become weaker, and at some point it will flip, and from weaker and then become stronger. So basically that's the pattern of intensity of the DEP force. And there are two types of force in DEP, which are negative DEP force and also positive DEP force, represented by the negative value in the curve and also positive DEP by the positive value of the curve. So basically, in positive DEP force, the particle will move attracted towards a region where the density of electric field is high, and in negative DEP force or NDEP, the particle will move away from the region of high electric field density. And the third thing is the point of frequency where the CMF value is 0. This is the point where what we call the crossover frequency. So in this crossover frequency, the positive DEP force and negative DEP force cancel each other out, so the force basically become null. So like I mentioned before, the CMF is everything in DEP. So what's the problem? The problem is in the context of trying to integrate AI into DEP device, CMF value is impractical. It's not practical. The value is not real. It comes from an equation. It doesn't even have a unit. So we need a numerical value that we can feed into the machine learning, to the AI, to make it become more make sense to the AI basically. So our solution is we need to translate the CMF curve into a numerical value. So how do we do it? Next. Okay. As I mentioned before, in the curve you can see that the force at lower frequency is strong and then become weaker. At some point it flip from weak and then become stronger again. So actually we can observe this in our actual experiment. So at 50 kilohertz, for example, the bacteria moves faster then 150 kilohertz, for example. And then at some point, the bacteria will move away from the edge of electrode. Initially, it will move away from the edge of electrode, and then at some point, it will flip and move towards the edge of electrode. So, in our simulation, the edge of electrode here is the region of high electric field density. So we can observe this, and we can calculate this velocity. So that's what we do. We choose a frequency point, and we measure the velocity in each of the point and plot into a graph, and then we can get this kind of curve. Notice the similarity between this curve and also the previous curve, the CMF curve, but it's basically the same curve, but this time we have a numerical velocity value in centimeter per second. So now we have a numerical value, something that is quantifiable, or as I say, a value that makes sense. Okay, this is one bacteria. So next. This is the combination of all 6 different bacteria into one velocity curve. So the part of AI integration is that there are 3 areas where the AI can try to recognize and differentiate different bacteria. First is we pick one point, for example this point, and the velocity of different bacteria will be different. Second area, there are differences in the crossover frequency between each bacteria. So the AI also can try to differentiate that bacteria from the crossover frequency. And finally, the overall changes of the speed. The AI can also use the data to try to recognize the type of bacteria. So what's the point of me saying using velocity and all this? What I'm trying to convey is that it is why is it that we need to build something new, something a new AI complicated system when we can use a system that is abundantly available in the industry today. So which is the velocity or speed recognition system. So all of this can be done using the velocity recognition system that is already being used in the industry. So for example, in the sport industry, they already use speed recognition. They can recognize every player on the field. They can know the speed of the player, movement speed of every player, and also speed recognition abundantly used in automotive industry and also shipping industry. So what's the benefit? The benefit is the integration will be easier. Instead of we asking the AI to learn this complicated equation, which is the DEP equation, now we can just ask the AI, the machine learning, to learn the velocity equation. So it will be very simple to integrate the AI into our system. The other benefit, the sensitivity is expected to be 90% sensitive, above 90%. And the detection time will be around 10 to 15 minutes compared to conventional bacteria detection method, which took 24 to 48 hours. And finally, the overall operation cost will be reduced because one DEP device can be used repeatedly. Okay, that's all. Thank you.
Okay, thank you very much, Muhammad Ahmad, for the very nice presentation. So now I will open the floor for any question. Okay.
Thank you, Atman, for your good presentation. I just want to ask, what other parameters besides velocity, because you're using velocity as the parameter that you're measuring,
Yes.
what other parameters that you can use to measure to describe this behavior? And then, do you consider temperature when you do this measurement?
Temperature, the first question, what are the parameters? Actually, we can also measure the force by using the force equation, but it's quite difficult. It's a bit more complicated, and I don't think there's any other parameters that is easier to measure besides velocity. And the temperature is not considered in our experiment because first we use a normal temperature, room temperature, and then I don't think the temperature will have any effect on the dielectrophoresis effect. Yes.
Okay. Is it? Answer the question. Okay. There's another one.
Hi, thank you for a nice talk. I just want to ask about, you mentioned different bacteria have different velocities, right?
Yes.
So what is the parameters that affect the velocity of the bacteria? Is it the dielectric property? So if it's the dielectric property, how does the behavior differs when we monitor something like a metallic materials, like maybe nanoparticles, metallic nanoparticles? Is it valid to also monitor it using dielectrophoresis?
Oh yes. It's will be into the more detailed DEP that I refuse to explain because it's quite complicated. But basically, the electrophoresis is affected by several parameters, which are in case of bacteria, there are 6, I believe. There are membrane electrical conductivity, membrane permittivity, cell size, cytoplasm permittivity, conductivity, and also cell wall permittivity, conductivity. All this that contribute in the charges of the surface and also charges inside the bacteria. So in case of bacteria, it's quite different because there are charges outside the bacteria and also inside the bacteria. So that one is affected by the affecting the movement of the bacteria when affected by DEP. But the point of this project is that we don't want to look at that parameters. We don't want to look at the CMF because it's tedious to conduct all of this because we need to find the exact value of all the parameters for the bacteria to determine the exact CMF. So yeah, so by doing the velocity, which it shows that also give a different value, making it like CMF value is not really reliable now. We can just use velocity. And for the metallic one, I believe we can because there are research using the EP on microplastic, for example. It's not a living organism. So if microplastic can be done, yes, metal also can be done because it's only involve charges, accumulation of charge on the surface of the particle.
Alright, thank you very much, Mr. Muhammad Ahmad. So, I'd like to give you a certificate for that. That's it.